meeting until 3:35. Is that right? 3:35. Okay. Y'all stop me at 3:35. I need to hit the road. Today matters because I've got class this evening. All right. I announced these to Bill, but I know Josh is interested too. The NJCAA District LM Tournament, or letters in there are words. I think that stands for National Junior College Athletic Association, is what my guess is for NJCAA. District LM, I don't know if we're District L and M or ladies and men. I have no idea what that stands for. Tournament for the volleyball team is this weekend, Friday, Saturday, and Sunday, up in Boaz, Alabama, Snead State Community College up there. Okay, so if you happen to be driving by Boaz over the weekend, stop in at Snead State and cheer the team to victory. Okay, and they're a really good team too. The postdoc at UAB sent this to Dr. Wilson that she said she was one of the newest cohort of merit scholars at UAB, whatever that means. She came across this 1-week summer opportunity for students interested in biopharma manufacturing careers, and thought that some of you may be interested. Students are paid $1,000 for a 1-week exposure to this, and they also pay travel expenses. So that's sometime in the summer. The deadline is sometime in January. If you want more information, I have the website and all the other things that you might need to know, or at least to find out what you need to know, or something like that. Okay. Let's get the slideshow set up from current slide. And I think we are recording. Okay. Now, we were dealing with reduction in order. Any questions before we get started today? Okay, we're dealing with reduction in order last time. We had talked and given an example of a general case. A second solution for reduction in order. Okay, and then we're on the top of page. This is Chapter 4, Higher Order Differential Equations, 4.2, Reduction of Order, and page 133, the general case. Okay, now, suppose we divide. Okay, now let's start off where we're supposed to do. Let's get back, and let me get my pen set up. Okay, here's where we're beginning. A2 of x, y double prime, plus A1 of x, y prime, plus A0 of x times y is equal to 0. There's our generic second order differential equation, linear differential equation. By saying linear, that means these a's are only functions of x's alone. They could be constants, but functions of x, no y's in them. And it's a homogeneous form, equals 0, general case. Okay? Now, suppose, and this is a trick we did before, divide everything by a sub 2. Okay. Now, hopefully you realize that's safe to do. What is it you never want to divide by? 0. But of course, if a of x was 0, this would be a second order differential equation. It would be a first order. So we're safe to say a sub 2 is not equal to 0. In fact, it can't be 0 for any value of x for this to happen. So with that in mind, we can do that. Okay? So that wipes out your coefficient here. So what we now have is y double prime plus, now this is just still a function of x, let's just call it a new name. Why not? Once you get used to a name, why not get a new one? P of x, y prime, plus, why don't we call this one q of x, because that's just a function of x, times y, and this, of course, is still 0, because if you divide 0 by anything other than 0, it's still 0. Okay? Now, here's the assumption here. P and Q are continuous on some interval I. Now, understand you just divided by A of x, A2 of x. Now, if A2 of x, say, was factorable, doesn't have to be, but what if it was, and you set each of those, okay, now, these may not be continuous everywhere, because everywhere you have a factor, you tend to have a, or you at least can have a discontinuity, okay? So for them to be continuous on I, that means you're limiting yourself to segments of that domain where these are continuous. But that's all that's required. It's just continuous on some interval. Doesn't have to be everything, just some interval. So they're continuous on I. Let's suppose further that y1 is a known solution. So we know y1 of x is a solution of this differential equation. Okay? You just happen to know that. Okay? But remember last time we knew that, you know, in example 1. So given that y1 is an example of this, find the rest of them. Okay? Well, let's just suppose we do know y1. Okay? On the same interval I. Okay? And that y1 is not equal to 0. Okay? We need to know that too for every x in the interval. For all x in I. Okay? That y1 can't be 0 there either. There's going to be a reason for that to show up later. Okay? Now, here's a good old trick again. Let's define your other solution y is equal to some u of x times this y1 of x. Okay? If we define y to be that, then it follows that, let's take the first derivative of it. What would that be? Y prime would be, you can leave off the of x's if you want to, u prime y1 plus y1 prime u. Right? Okay. Product rule. Okay? Let's do it again. Y double prime then would be u double prime y1 plus y double prime, that y1 double prime u. Okay, you left off 2. You got a product rule here and a product rule here. Clever of you to put on this y1 prime u prime plus y1 prime u prime again. Oh, clever of you to put them there together. So this would be 2 of them. So this y double prime is equal to u double prime y1 plus 2 y1 prime u prime plus y1 double prime u, or something like that. Okay. Now, if we start combining these things together with what we've got there, this y double prime here will now be, now I'm going to erase this continuous part because we're given that. We'll probably need it later, but I don't have room for it now. So get out of there. Okay. All right, this y double prime is u double prime y1 plus 2y1 prime u prime plus y1 double prime u plus p of x times y prime, which is u prime y1 plus p, I'm not going to put the of x in there, y1 prime u, plus q u y1. Duh. Okay. Now, because we already know that y1 is a solution to this equation right here, we know it. They told us it was. And we believe them. We're trusting souls. Okay. If that's a solution, then you know that if you factor a u out of here, you wind up with a y1 double prime, factor a u out of this one, and you have plus p y1 prime plus q y1, okay? All that is times u, because you factor the u out of this term, that term, and that term, okay? But guess what this is? That's 0, right? Because this was a solution of that differential equation, so that's 0. Gone. Okay? What do we have left? U double prime y1 plus 2y1 u prime, y1 prime, u prime. That one we got rid of. Okay? Plus p u prime y1. And that's all, isn't it? Okay? I forgot to put it. That's equal to 0. We're just plugging in. The first part was 0. This is what's left over. Okay? Now, if you'll notice here, you got a u double prime y1. Yeah, get out of there. Okay? Plus 2 y1 prime plus y1 times u prime is equal to 0. I think that's where I want to go with it. Okay? Now, as if we haven't made enough substitutions now, let's make a new one. Let's say, let W equal U prime. Why not? Oh, where did the P go? The P went away because it wasn't happy with us anymore. Okay, there it is. Didn't you see it? Right there.
I was like, maybe you just did something I didn't notice.
Okay, no, sorry about that. Good catch. Okay? Now, if you let W equal U prime, what do you have now? You have Y1 W prime, because if W is U prime, W prime is U double prime, right? So this would be a Y1 double prime plus this thing, which is 2Y1 prime plus PY1 with the P in there, times W. And that's equal to 0. Well, what have we just done? We've reduced the order from a double second derivative to a first derivative. Wasn't that fun? Okay. Now, it's linear. There's no W's in y1, and then there's no W's in, or W primes or anything else in the parenthetical expression there. It's linear, it's first order, and believe it or not, it's separable. Okay? So let's see what we've got here. W prime over W is equal to, now I've got to negate some things here, but that's okay too, the minus two y1 prime over y1 plus p. Okay, because the y1 here and that y1 would divide out. Oh, this is all, let's see. Either put it in parentheses or make them both negative. I don't care which, too much. Okay, I made them both negative. Okay, but that's separable. Okay? Now, if that wasn't bad enough, okay, let's do this. Rather bizarre how they do it, but it's okay. They left them all on one side, and I guess I could have too. You still separated, but I'll put them back on one side. I really need more room. So let me find some places to erase. I'm not sure that I need this anymore. Well, my eraser didn't come up, so I was erasing with the pointer. There we have it. Okay, with the whatever they call that other device. Oh, I've already erased what it is. Okay. I'm going to leave that one. I'll erase this one. Okay, I'll erase this one. And that one. Okay. I probably could erase some over there, but it's disjointed, so I'll leave it there. Okay. So we'll bring them back together and integrate each one of them. Well, this just simply gives you, integrating this first one is, any ideas? Isn't that log W? Okay. And if we brought this to the other side, then that would be plus 2 times log of y1. That we know what it is, we just don't know what it is, okay? And then we have a plus, now, the integral. Now this isn't a double prime here, I don't know what that is. Oh, let me erase some of that, because that is getting confusing. That's not in there. Minus p, okay. Because remember, it divided out, the y1 divided out when we divided by that, okay? So it's just p. So that's the integral of p of x dx. Okay, and that's equal to 0. All right, we can, well, let's first do this. Change this 2 log y to log y1 squared. Okay? That's legal in most states, right? Okay. And then we can combine these to be the log of absolute value w y1 squared. And guess what? Isn't that equal to, or the minus of this equal to the integral? I don't know. We don't want to do that, I don't think, do we? Yeah, we do. Maybe. Kinda. I don't know why it wouldn't work. Yeah, I think it would. Now, we didn't do a constant in there, so if we had a constant, let's just make it plus log c, okay? Combine that with the others, so we have the c in here, okay? And that's equal to the integral of p of x dx, which you've sort of seen before in a different context, but it was different p, of course, too, and everything. Now, let's e both sides. Why not? Well, let's see. Where did the minus come from? Did I just make that up? No, I think the minus belonged over here, so let's not put it there. Now let's e both sides, and we have no, they did the constant on this side. Sorry about that. I'm sorry. And they incorporated the negative sign with the constant. Okay. No, I'm sorry. The minus sign is there, and then they put a plus c out here. Okay. I think. We'll get to that in a minute. It may have been a log c. Okay, whatever it is. Now let's e both sides, and you have w y1 squared is equal to e to the minus integral p of x dx. That looks awfully familiar, doesn't it? Okay. And when you did this one, they combined it over here and put the c in front here. I mean, however they did it. Okay. Now, let's isolate the w. So we'll divide everything by y1 squared. So w of x is equal to c e to the minus integral of p of x dx over y1 squared. Okay? Now, what was your w? I hope I left it. Yeah, there it is. It's y is that's equal to u prime. Okay? So, we're going to integrate again. We're going to call this C1 now because we're going to need another C in here. Okay? W is equal to u prime, which is du. And I'll put my is equal to C1 e to the minus integral of p of x dx over y squared, or that's y1 squared, I believe it is. Okay? And then this is times dx. And when you integrate that, you have integrate both sides of this, you get u is equal to, let's pull the C1 out, and that will be the integral of e to the minus integral of p of x dx over y1 squared plus some other constant, let's call that C2. Okay. Now, here's the part that just about drives me nuts. By choosing C1 equal 1 and C2 equals 0, where do you get that? But they're arbitrary constants, remember? So pick anything you want. So it seems like, why did we go to all that trouble to mess with them if you go to them? Or did you just, well, never mind. Okay. And what was your u, by the way? The u was y over y1. Okay. So we have and let's call that y2 now. Why not? Okay. So this will be y2. I'm going to multiply everything by y1 if I can get it to stay on the screen. That's not squared, it's y2. But the screen went out just when I was writing it, so I couldn't see where the y was. y2 is equal to y1. Now we chose C1 to be 1, so we've gotten rid of that, of x times this integral right there. I'm not going to write it again. Okay. And we chose that one to be 0. So this integral right here, we'll put right there. I love the next little statement here. It makes a good review of differentiation to verify that this function, it satisfies equation 3, and that y1 and y2 are linearly independent on the interval in which y1 is not 0. Yeah, right. Okay. And they just leave it there. Okay. Now they go to example 2, and I guess they expect you to use it. So let's do. And I'm going to have to erase all this and put back up just what I need, because this is just way too crowded. So let's do example 2. Okay. Here's a function. y1 is equal to x squared. They say that is a solution of this differential equation. X squared y double prime minus 3x y prime plus 4y is equal to 0. Okay? And have I told you before I'm a cynic? Okay, I am. I want to make sure that's right. So let's do it quickly. y1 prime would be 2x, and y1 double prime would be 2. So let's see. Here we have 2x squared, agreed? Okay, minus 3x times 2x minus 6x squared plus 4x squared, and sure enough that does equal 0. Okay, I'm satisfied. That is a solution. All right. What's that?
We're done.
That's a solution. We need to find the general solution. Okay, so we're through with that. That is a solution. You've solved my cynicism. Okay, made sure it was correct, and it is. So let's get back to find the general solution of that differential equation. Okay, now we've verified that is. Now remember the first thing we did? Up above, get rid of the coefficient, just like we did for first order. Second, as long as x is not equal to 0, you're absolutely right. But if x is equal to 0, this is not a second order differential equation.
But it can't be negative either. So
It can't be negative either. Well, I see no reason that it, okay, yeah, it can.
well, they just said from 0 to infinity.
What's that?
They said from 0 to infinity.
Yeah, so, but not counting 0. So
Right.
you could choose one side or the other. They chose the positive side. Keep on the right side, the positive side. Okay. So let's first divide by x squared. Okay. So what we have now is y double prime minus 3 over x y prime plus 4 over x squared y equals 0. Okay? Now, that's a linear second order differential equation in y. It's not linear in x, obviously, but nothing ever requires you to be linear in x. Okay? And it says find it on the interval 0 to infinity. It may be good in both directions, but it definitely is not good at 0, so you have to choose an interval, one side or the other of 0. So they're choosing on 0 to infinity. Okay, should be good everywhere there. Okay. Now, there's our standard form. Okay. Now, what did we do? What did we determine before? y2, looking up above, y2 is equal to y1, which was x squared, times the integral of, okay, we got a little bit of scratching around to do here, okay? Your p of x was your coefficient of your y prime, coefficient function of the y prime. So that would be the integral of e I'm going to write it down first, and then I'm going to plug in. E to the minus integral of p of x dx, okay, over y1 squared x. And then that's times dx. This dx is with that integral, that one's with that one, okay? So let's take a point at a time. Your p of x is equal to minus 3 over x. Agreed? Okay. Then let's integrate that. Integral of this is the integral of that, and that would be a minus 3 times log of x. We're not going to do a plus c, remember? We don't do a plus c here. Let's rewrite this as log x to the minus 3. That's probably not the best way to write it. They keep the minus on the outside. I don't know if it matters. Let's keep the minus out here and make that a plus 3. Okay. No, actually what they do, they keep the minus 3 here and do that. Frankly, I don't know why they do that. It seems so awkward. Oh, wait. You have a minus sign here, and you have a minus sign there. So let those two minuses go away. So let's do it here. So this will be x squared times the integral of e to the minus and a minus 3, so that'd be e, and they keep the 3 here, of natural log of x. But they've got to go on and do it the next step. Why didn't they do it earlier? Yeah. I'm in favor of doing it. Let's do the e to that, and that's going to be, the minus sign comes out here, and this is just x cubed. E to the x cubed, e to the log x cubed, with the minus sign out in front. This is minus x cubed. But the minus and times the minus is a plus, times this minus. So that's going to be x cubed up there. And this denominator is x to the 4th dx. Hey, this gives us x squared times the integral of, well, we don't need the integral. That's just log x, right? Okay. And I guess somewhere in here we have a plus c, okay? Or they just leave off those. So I don't know what they do with them. Okay?
Not this.
So it's just x squared log x. Okay? So there is our y2. And here's what they do with the constants. They just wait and put them in now. Okay? So your general solution, y, is equal to c1 x squared plus c2 x squared log x. Okay. Yeah. And that's how they leave it. Okay. Now, number 1, that's good. It's not good at 0, but we knew it couldn't be 0. But now we see why they chose the positive side. Because you can't put a negative in here. Okay? So yes, we feel nice and warm and fuzzy about it being from 0 to positive infinity, because that works separately. Okay. Now, that's all she wrote for 4.2. No, 4.3. It's 4.2. Okay. They do have some remarks at the end, and I say knock yourself out with them. I don't see any real thing major that we need to associate, so let's just go on. Homework exercises here. Do any of the odds, 1 through 15. They have a whole bunch of them here, and that's any of those that you find answers in the back, do. Then 17 or 19, if you find answers in the back there, do them. 21, if you find answers in the back, do it. 23, I doubt if there's an answer back there, but if there is, you can do it. And a computer lab assignment, I don't have a computer lab, so I don't make the assignment. If you have access to something you want to play around with that, you certainly can. All right. Now we're ready for 4.3. Finally. We're through all the preliminaries. Let's actually start solving some differential equations. Now, how are we going to do it? We're going to do linear equations, and these are higher order linear equations. We already know how to do second order. So first order. I don't know why that just chose to go out. Okay, now it came back. Okay. But we're going to do the homogeneous case. This is where the right-hand side is equal to 0. Okay? And we're going to limit ourselves to constant coefficients now. Later we'll try variable coefficients, but now we're going to do constant coefficients. Okay. As a means of motivating the discussion in this section, let's return to first-order differential equations, more specifically to homogeneous linear equation, a y prime plus by equals 0. Okay? Very simple. Okay? Now, of course, this a cannot equal 0. Otherwise, it's not a differential equation. If A was 0, then that would just be by is equal to 0. Y would have to be 0. Not a very interesting problem at all. Okay? B is just any constant in the world. Positive, negative, fraction, decimal, rational, irrational, it doesn't matter. Now, you can solve that either by separation of variables or with the aid of an integrating factor. But there is another solution method, one that uses only algebra. Okay? But before illustrating this, we'll make an observation. Solving that equation yields y prime is equal to ky. Okay? Y prime is equal to k times y. Now, where does that come from? Let's subtract by from both sides, and you get ay prime is equal to minus by. Divide both sides by a because it can't be 0. And you have y prime is equal to some constant times y. Okay. Constant happens to be minus b over a, but who cares? It's just a constant. Okay? Now, that observation reveals the nature of the unknown solution y. The only non-trivial elementary function whose derivative is a constant multiple of itself is what? Yeah. The only function y whose derivative is a multiple of itself is what? Second? E to the something. E to the kx, in fact, isn't it? Because if y is equal to e to the kx, then y prime is, guess what? Take a derivative of it. K times e to the kx, which of course would be k times y, because y is e to the kx. Okay? Now, but for some reason, some completely unknown reason, they now choose to call it an mx, okay, which is fine, just m is equal to k. Okay. Now, if you plug that in to our original up here, okay, so they're going to call this y is equal to, I'm sorry, right here, y is equal to e to the mx, okay, and then this would be y prime was m, okay. So, with that here in play, you have a, y prime is m, a m e to the mx plus b e to the mx is equal to 0. Okay? When you plug that in, y is equal to e to the mx, that means y prime is m e to the mx. Those are really ugly. I probably should do a nicer job of that. Okay. Y is equal to e to the mx. Y prime is m e to the mx, which is m times y. You don't have to put that in there, but I did. Okay, you plug those into the original equation. AM, that's morning time, e to the mx plus b e to the mx is equal to 0. Well, obviously, you can factor out an e to the mx from both of those, right? Leaving you am plus b is equal to 0. Now, here's where the magic happens, as if it hadn't already happened. e to the mx is never, ever equal to 0. Picture an exponential function, always positive. Whichever way it's going, never equals 0. So that means this thing has to be 0. And guess what that means? M is equal to minus b over a, which we had at the very beginning there. And I said, but they're not going to pay any attention to that now. Okay? So M is equal to minus b over a. But that's your one and only solution here. So that then is how we solve that equation. Okay? So they can sure beat something really easy into a mess. All right. Here's one. 2y prime plus 5y is equal to 0. Okay? What can we conclude from what we just did? Well, we said y is equal to e to the mx was the solution, right? That's what we concluded. What did we say the m was going to be? It's minus 5 over 2, right? So we know our solution, y is equal to e to the minus 5 halves x. Okay? And you can do an arbitrary coefficient of c. You can make it c, but you can put it in front just as easily as anywhere else. And that is your solution. Okay? Now, let's step it up a bunch of notches here and have a sub n. That's just a coefficient. That's not a function of x. A sub n, y, the nth derivative of y. So this is nth order linear plus a sub n minus 1, y to the n minus first derivative of y, plus, they're going to skip a few, so I will too, dot, 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 plus, and go down to a sub 2, y double prime, plus a sub 1, y prime, plus a sub 0, y is equal to 0. Remember, we're doing homogeneous cases here. Okay? Now, all those a's are constants, okay? Real constants. No variables in them. Certainly no x's. Absolutely no y's. They wouldn't be linear. Of course, the a sub n cannot equal 0. Okay? All the rest of them could be anything else. They could be 0. Now, that's going to be our generic equation for much of this section. So just sort of get that implanted in your mind. And we're going to step back and go to a second order. Okay? We did a first order. We did the nth order. Now we're going to step back and do the second order. This really makes a lot of sense, doesn't it? So let's do this one. A, y double prime plus b, we're not going to use sub n's because we only have 3 of them, y prime plus cy is equal to 0. Okay? Constant coefficients. What would be a good guess for what a solution would be? Y is equal to, just like we did before, e to the mx. Second? Yeah. Because all these are constant coefficients, all the y's and y primes and everything else, it better have e's in them, because if they have anything else, they're not necessarily going to add to 0. So let's just assume y equal to e to the mx is your solution. Okay? Now, can someone suggest to me what the polynomial equation is going to be. Now, we can work it out if you want to. I'll be glad to do that. But can anyone make a guess? Well, they do it, so let's do it. Okay? If that's the case, what's your y prime? M e to the mx. And what's your y double prime? E to the mx. So if you plug in here, what do you get? A m squared e to the mx plus b m e to the mx plus c e to the mx, okay, is equal to 0. What can you factor out of every term? E to the mx. And what's left? C is equal to 0. And again we say, e to the mx ever be 0? No. So, e is always positive. It's never 0. Okay? E is always positive, never 0. So therefore, it concludes that am squared plus bm plus c has to equal 0. Okay? It has to be that. That's a quadratic equation in M. And guess what we can do with it? Yeah, we can either factor it if it's factorable, if not, use the quadratic formula. But we can come up with 2 values for M. If there are 2. There may be none. There may only be 1. But there can't be any more than 2. But you can come up with 2 values for M, and then plug those back in here, and one of them will be the first one, e to the first mx, the other one will be e to the second one. Then you put arbitrary coefficients with them, you got your general solutions. Okay? This right here, that quadratic equation, is called your auxiliary equation. This thing right here is called the auxiliary equation. Okay. Okay, auxiliary equation. Now, let's say we can't factor them. Okay? So we use the quadratic formula. Anyone remember? I think I'll start on a clean page, okay? I'll rewrite that equation. Okay? am squared plus bm plus c equals 0. Okay? What does your quadratic formula tell you? M is equal to minus b plus or minus square root of b squared minus 4ac all over 2a. Right? Y'all remember that well, didn't you? Okay. Huh? You hate it? It's so nice. Okay. Now, I don't know if you remember, but we said everything in the world hangs on that, what they call the discriminant. What's under the radical? Okay? Because if what's under the radical happens to be b squared minus 4ac happens to be less than 0, guess what? No real solutions. They're all imaginary. No real solutions. All complex or with imaginary parts, because real numbers are complex. Okay. What if b squared minus 4ac happens to be equal to 0? Second?
Can't do that.
Oh, yeah. That could wind up equals 0.
Two real solutions.
Yeah, you only have one solution. One
Oh, okay.
real solution, and that real solution is m is equal to minus b over 2a, right? That's the only solution you have. What if b squared minus 4ac is greater than 0? You have two real solutions then. Two real solutions. Okay?
Will they always be solutions, or will sometimes one be a solution, one won't?
No, they'll always be, yeah. Quadratic formula that you hate is good that way. They're always solutions. They may not be real, okay? And you may only have one, but there's always two. Now that middle case, that's often called a repeated solution. It's itself and itself again. It would be like x minus 3 squared, or m minus 3 squared. That would be m equal 3 or m equal 3. Same solution as a double root, okay? But it's only one solution, okay? Now, we're going to call these cases, okay? In this case, m1 and m2 are both real. So we're going to call that case 1. Case 2 is they're both real but equal. So this will be case 2. It's real, but the two solutions are the same solution, right? Double root. And case 3 is they're oh, and by the way, when these are no real solutions, they're complex, they're always complex conjugates of each other. Remember, this would turn out then minus b over 2a, that's a real part, plus or minus this thing in parentheses in the radical is negative, so that would be basically 4ac minus b squared times I. Now this I is not your vector I, this is your imaginary component, and that's also, it's the square root of that over 2a, okay? But these are complex conjugates of each other. P plus qi, plus or minus qi. Always complex conjugates of each other. Okay, so let's start with the first one, the easy one. Case 1. Two real solutions. Here's your general solution to that second order, ordinary, linear, differential equation with constant coefficients. Okay? It would be y is equal to C1, your arbitrary coefficient, e to the m1x, where m1 is one of these solutions, plus C2, e to the m2x, where there's your second real solution. C1 and C2, arbitrary coefficients. All right. Now, case 2. One real solution is a repeated root. Only one. Okay? There your solution would be this. Y is equal to C1 e to the whatever this turns out to. I'm just going to call it mx because that was your m here. It's minus b over 2a is what the m is, by the way. Okay? So that's your mx. Plus C2. Now, here's what they do. Remember that whole rigmarole about reduction and blah, 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 okay, that we did in 4.2? Turn back to 4.2. Basically what you turned out with is something multiplied by your first one, okay? And different things, it was different values, but they lead you back to what you did there, and what the integral turns out being is integral of x dx, which is what? No, it's just x. Integral of, no, I'm sorry, I said it wrong. Integral of dx, that's what I meant to say. Integral of dx is just x. So your C2 is going to be, your y, your second general solution is y is equal to C2 x e to the mx. You only have one m, so you do 1 C1 e to the mx. The second one is C2 x e to the mx, because that's your basically reducing function. It's just the function x, because the integral comes out the integral of dx, which is just x. All right. Now, the case 3 is kind of a real issue. And they skip so many steps. Surprise, surprise. And it's easy to get bogged down. And I don't know. I don't know whether to bog you down with it or to just say take their word for it. But now remember, here are our first two cases. Two real roots, m is equal 1, m is the other, c1e to the m1x plus c2e to the m2x. That's it. That's it. If you have one and only one root, a double root, c1e to the mx plus c2x e to the mx. Okay. Now, getting rid of that. What if you're, and okay, what are we going to today? 40? No, 35. Yeah, 10 minutes, 35, right? Okay, stop me before I get to 35. I'll try to get as much of this done as I can. So you have two complex roots, okay? And I'm just going to call them, I'll do what the book says. M1 is equal to an alpha plus I beta, or alpha and betas are just numbers, and your M2 was alpha minus I beta. Because remember, they're complex conjugates of each other. Alphas are real numbers, betas are real numbers, it's just one is a complex, put the I with the beta, and it's plus or minus. Complex conjugates of each other. Okay. Now, here would be your solution. And they are your solutions. It's just really awkward. Now, for some reason, they go to capital C's here, and there's not a real reason why. I guess they're suggesting that they could be complex coefficients, but I don't think that's the case. So I'm going to do what the book says. C1 e to the alpha plus I beta x plus C, capital C2 e to the alpha minus I beta x. Just like we did before, M1, M2, right? All right. You could use those as your solutions, but they're pains in the neck to try to keep up with all that. However, in practice, we prefer to work with the real functions instead of complex exponents, and to this end, we use Euler's formula. Now, here's Euler's formula. Euler was quite a character to come up with this. He came up with so many incredible expressions. E to the I theta, okay, is equal to cosine theta plus I sine theta. Now, we can't derive Euler's formula there, but that is a formula in nature. It's true. Amazing, but true. E to the I theta is cosine theta plus I sine theta. Okay? Now, where theta is any real number. Okay? And by the way, they say you can do this using a Maclaurin series. Oh, yes, I want to do that. Okay. But anyway, that's what it is. Okay? Where theta is any real number. So therefore, this thing right here, okay, this thing right here could be written as e to the alpha x, e to the I beta x. Remember that? And saying raised to a power, a sum of two powers, yeah, is the product of, yeah, 7 to the 8th power is 7 to the 6th power times 7 to the 2nd power, right? Same base, add the exponents, you multiply those, right? Okay with that? Okay. This is real. Everything there is real. So don't worry about it. We're only going to mess with this complex part. Okay? So, the e to the I beta here be e to the I beta x will be cosine beta x plus I times the sine of beta x. Okay? All right, so you got rid of one I, got one real part. Okay, this is a real part. Don't forget that. Now this is a real part, and you got that one. Well, let's see. Let's do the other one. And again, here you would have e to the alpha x. That's the same alpha x as we have there. That's a real part. So hang on to that one for a minute. But let's do this part, e to the minus I beta x. Well, that would be cosine of minus beta x, right? Plus I to the sine of minus beta x. Agreed? Yeah? Okay. Now, remember, cosine is what kind of, I'll get you to agree to anything. Okay. Okay, it's not necessarily positive, but even. And e to the beta x and e to the minus beta x are the same values. So these are both equal to cosine beta x. But guess what this does? If you add those two, what is sine? Odd. So this is minus I sine of beta x, right? Now, so basically this becomes, the second one now becomes e to the minus I beta x is equal to cosine beta x minus I times the sine of beta x. Okay. All we did was take the minus here and kind of move it out front is what it looks like we did. Okay. Now, if we were to add these two together, now, what they've said here, they haven't said it, but what effectively they're doing is letting C1 and C2 both equal 1. Okay? And then they're going to turn around and let them C1 equal 1 and C2 equal minus 1. And what happens when they do that magical thing here, you get two solutions. And you add them together, and we're running out of time. So, believe it or not, this is what you come out with. Okay? Because you see, something's going to go away here. And if you add the two, these go away. If you subtract the two, those go away because they're the same thing. So, after all of our mess here, here's what it comes out being. Y is equal to C1. Now this is a little c1, a constant coefficient. Remember the e to the alpha x? That was real and it's in both of those. So that's there. Then you have a cosine beta x, and your second one is C2 e to the alpha x. That's still there. Sine beta x. Okay. Now, actually, an easy way to write that is e to the alpha x, because that's in both terms here, times C1 cosine beta x plus C2 sine beta x. Those are your two solutions anytime you have two complex conjugate roots. Your m are two complex conjugates. The real part you put as the e to the alpha x out front. The imaginary part you put as the coefficient of your x in C1 cosine beta x and C2 sine beta x. Real solutions for your complex roots. A lot easier to work with. Okay? And I'm sorry we don't have time to slug through all this, but I'll just tell you, they come up with one of those very arbitrary and confusing sounding things. Well, let's just let the C1 and C2 be 1. And then let C1 be 1 and C2 be minus 1. And you think, how can you do this? Why can you do it? But you can't. And they did. And when you do one goes away, do the other, then you combine them, and you lose the imaginary parts completely. Okay? And that's what you get. Bottom line. Now, repeatedly, we'll be coming back to these three cases. So sort of get used to them. They're there. They're fun. They are all over the place. I don't think we're going to have time to do example 1, are we?
No.
Okay.
I was hoping at the end of this it'd be like, yeah, don't worry about memorizing any of this.
Basically, we're going to use it enough that you're not going to be memorizing it. You'll just know it by heart. Just like your name. Did you ever sit down and memorize a name? No, people just called you that so much that after a while you knew that was you. Okay? Yeah.
It won't be bad if you got to use it all the time.
Yeah. I swear, our dog knows certain words. She comes up to me every evening and puts her paw up in my lap. And I say, well, what, you want me to get on the floor with you? She goes, gets her toy, and waits for me to get on the floor with her. She knows that phrase. She didn't memorize it, but we use it every night because I get tired of her putting her paw up on me. So I say, you want me to get on the floor with her? And then she lays down for me to scratch her or whatever, It's every night. So there's example 1. We didn't get a chance to do enough to do any examples, so there's no new homework exercises here, but we'll begin with example 1 next time. Then we'll do an initial value problem, third order differential equation, fourth order differential equation, and then some rational roots. Oh, we got a lot of fun to do. Okay. We're going to be using everything you did in pre-calculus algebra about finding zeros. We're going to be doing it. Well, maybe not everything, but a lot of the stuff.
Good, because I remember reading that.
Well, good. We'll be refreshing it. Okay. All right. And Corey never showed up, so let me mark him here. Let me get things taken down here. Let's see.